介绍一下，赵丁老师现在是梅基梅隆的助理教授，然后他同时是在机械工程系，还有那个计算机系以及机器人系几个系的一个交叉。然后赵老师现在是在领导了卡梅基梅隆的 Safe AI Lab，然后他的研究呢，是专注于关于那个 AI 安全与应用的理论，还有那个实践方面的。那么应用会包括这个自动驾驶辅助型机器人医疗诊断等等等等。那么赵老师还获得了啊 NSF 的那个 Career Award，以及 MIT 的35 Under 35的 Award 等等。然后赵老师其实现在在国内，其实赵老师是几周之前呢是想做一个线下的一个报告，然后跟北大的同学们都线下见一下面，聊一聊。但是因为疫情的原因吧，然后隔离了19天，就有点没办法了。然后可能就今天就不得不就是先给大家一个线上的一个报告吧。然后大老师周末就回去了，但是没所谓，我们都可以在线上的来做更多的一些交流。然后赵老师也通常会招很多博士嘛，所以如果大家对读博感兴趣的，我觉得都可以去联系一下赵老师。好，下面时间交给赵老师了。
好，谢谢。So I still will present in English, so it will
嗯
be easier for me. So let me share my screen. Can start. Can you see my screen?
Yes.
Okay, great. So very happy, it's a great honor for me to discuss this topic with you guys. So today I want to talk about the safety and the generalizability of trustworthy intelligent autonomy. So first, I want to discuss what is trustworthy AI. It's actually the word that has been used by European Union. So they say to maximize the benefit of AI system, while at the same time preventing and minimizing the risks. You can also notice that from US to the European, from to the Europe, they all pay a lot of attention to the trustworthy AI, or called safe artificial intelligence. So for example, in the US, the National Science and Technology Council, they list safe AI is one of the critical and emerging technologies because its potential to protect the security of American people, expand economic prosperity and opportunity, and realize and defend democratic values. And also the US National Institute of Standards and Technology and the European Commission should stand up to join a research institute to tackle several fundamental elements to ensure trustworthy AI. So this is also, it's a think tank called Center for New American Security. They published this suggestion just a few months ago. On the right, you can see, so trustworthy vehicles, or more broadly, trustworthy autonomy, is also become very popular research direction. For example, this is also published by European Union. So they say they have a full size more than 80 pages of report about how to design the trustworthy autonomous vehicles. So who else care about AI safety? So for example, on the top layer, you can see those are companies. They all have the groups for trustworthy AI. Well, US National Science Foundation has established two centers for trustworthy AI, and Stanford, University of Pennsylvania also have the centers. And also this NGO called the Future of Life, launched by Elon Musk. So our lab also want to also focus on the trustworthy intelligent autonomy for consequential applications by bridging fundamental learning theories and practical technologies. And particularly, I want to, my understanding of trustworthy AI is this, because whenever we make a decision, we have the environment, we have the our requirement, and also the algorithm. itself. So in this category, in this diagram, you can see there are many aspects of trustworthy AI. And today, particularly, I want to focus on two aspects. One, safety, another is generalization. So if you're interested in more of those concepts, including embodiment, explainability, evaluation, and human centricity, you can check my course. So all the materials are online for this course. So let's dive in for this two topic. So safety, I will give two examples of safety and also two examples of generalizability. Generalizability. So for example, for safety, we are founded by National Science Foundation, Uber, Ford, and Rolls-Royce, and Toyota. And for generalizability, you can see it's mostly found by some IT companies. For example, in safety, when in 2018, when Uber has the world's first fatal accident, so I was invited to investigate with them. So I will talk about this. So the background is that how we can evaluate a autonomous vehicle for safety. The challenge is when we test autonomous vehicle, safety usually is very rare. Safety event is usually very rare. So we need a very efficient algorithm to do so. So how to do that? Usually we collect the data from the real world. You just put the car on public street, and then do the event. Then we can build a stochastic model. In this case, for example, every million miles, you will have 2 accidents on average in the US. However, this is too inefficient. To make this more efficient, we need to skew the statistic of the surrounding cars and make this environment more severe. In this case, we want to do two things. One is that we want to evaluate the benefit or the risk in the real world, and second, we want to find the critical accident cases and the probability for those edge cases. And particularly, we want to use the result from this accelerated environment in this naturalistic environment. So to do so, we need 3 techniques. So first, how to model the environment. So we need a generative model or metaverse. And then second, we need we need to understand the failure cases. And also we want to do this linkage between those accelerated environment to the normal environment. And third, we need to be able to deploy those tests in the physical world. So there's an example to say how we can do this. So this is MCity is a testing facility at Michigan before I joined SMU. And you can see people use one automated vehicle to test another automated vehicle. In this case, we need to decide how this background car need to interact with another vehicle. So how to do so? So there is quite a few. I built a series of methods. So for example, at the beginning we said we need to be rigorous. So I have this important sampling listed, and then a heuristic method. And then first I want to have this heuristic method to make it more efficient. And then I make it more rigorous by introduce this important sampling. And third, I will try to have this adaptivity capability, and then later on need to make it to be more to tackle the dynamic environment, and also I want to make it more robust and work with high dimension. So there is those are each leaves are papers in this direction, and we already published some white paper about this work, and now the work is used as a standard protocol at MCity. And now I'm also working with this ISO standard for test scenarios and automated driving system with the ISO Institute. So, so this is how first to work with the safe AI, you need to first be able to evaluate and assess the safety of it. And the most important part is the rarity. And second, so how then after that we need to design the the safe AI. And one way is to design a user reinforcement learning tool to learn safe policy. So you can see reinforcement learning has been used in a lot of the cases like Atari or Go games. However, it has not yet been deployed to the real world like autonomous vehicles or AI assisted surgery robot because they are quite consequential. However, if we still do not use that for reinforcement learning for those applications, we may lose the chance to make the algorithm or robot more intelligent. So people has started to think about it and build some platform to test it. For example, this OpenAI have this called safety gym. And in this case, those robots will move around and try to avoid this blue dots and reach this green cylinder. So there is a different agent like a dot or car or this quadrupedal. So this safe AI provides some benchmarks with this usually use a Lagrangian approach. So the Lagrangian approach is the approach with some reinforcement algorithm plus the Lagrangian multiplier algorithm to add the constraints to it. So what's the limit of Lagrangian method or primary dual method is because we need to learn a proper learning rate for this Lagrangian multiplier. So a proper learning rate can improper learning rate can usually lead to oscillation, and it's hard to converge. You can see this is all kinds of Lagrangian multiplier during a reinforcement training. So in this case, there is a this oscillation is very annoying and sometimes it's very difficult to tune. So it lacks of optimality and feasibility guarantee. So in our paper, we propose a variational convex opposition to replace such a Lagrangian multiplier. So it has two steps, the E step and M step. So in the E step, so different from this primary dual methods in the standard Lagrangian multiplier. So we have this E and M. In the E step, we create a variational policy. That's a non-parametric policy. In this case, we can prove that this step with a proper definition of this variational policy, we can prove under mild condition is actually a convex optimization. So it's actually very helpful to generate such a policy. And then, so we can guarantee the optimality. And after we have this variational policy, we can go through this M step. In this M step, so we will have, because we just need to match the deep learning policy with this variational policy, which is just a table. So in this case, it's just a supervised learning. So the benefit includes it's very sample efficient and it's stable and because it's a convex opposition, and also the optimality can be guaranteed for each policy update. And we say, okay, so for each policy update, so we have the worst case is bounded. The efficiency shows it can be shown in this figure. You can see our method is the middle, and on the left you see all those policy that is on policy. On the right is the off policy. For the off policy, none of them achieve this cost threshold because we need to define the safety as the cost is below some threshold. Here is 20 or 10. So these are different environment. So you can see most of the cases, the old policy, they cannot touch this threshold at all. So they are failed. They are not safe. For the on policy, it can barely touch this boundary, which is fine. However, they are very inefficient compared to our method. So you can see on the right, so this is an example. Our method is this right one, and those other methods are other on-policy approaches. You can see they are actually they may eventually learn how to do this, but it's very inefficient. And pay attention. Note that the x-axis is actually in the log scale. So we are actually several order of magnitude, like 1,000, 100 times, 1,000 times more efficient than other methods that can also achieve the safety. So this is actually and this cumulative cost mean. So basically, this means for example, in the case of a self-driving car, so the y-axis means could mean that the car learn how to drive, while the x-axis means how many accidents you need to make to learn how to drive. In this case, our approach is more efficient, like 1,000 times more efficient, fewer collisions we need to make before we learn how to drive. So this is basically I think this is very important. So we can learn from the mistakes much more efficient. So these are the some of our environment. For example, this is a simpler environment called circle. So we just learn to go around the circle while try to avoid those yellow bars. So this, you can see this is our final result. And then this is a much more complicated, because you need to touch those dots one by one, and this yellow dots one by one, while try to avoid this moving obstacle. And also there's some stack obstacle like this blue one. So the car can learn this. To me, it's much more complicated. So this is our first paper on safety I want to mention. Another one is the safe RL. The has a inherited issue about robustness. So let's try to introduce. Let me try to introduce some concept to help you understand. So this diagram, you can see the x-axis is a reward value function of the reward, and the y-axis is the cost function. The value function for the cost for a policy. So any dot on this diagram represents a policy. And if because we need to design safe reinforcement learning, so the policy need to be below a threshold, meaning the cost needs to be below a threshold. In this case, this shadowed zone is actually all the feasible policy. We call this set is a feasible set, and this property we call it feasibility. And then we say, we want to achieve the best performance, so we want to maximize the reward as much as possible. So we want this dot to be able to move to the right direction, right? So this dot, among all the feasible policy, this dot is actually the optimal policy. So this is called optimality. And the third is called temptation. So we say the temptation, meaning if the shape of this set, the whole policy set is in this case, so the gradient of this boundary is positive, then we actually have this temptation that the dot want to go to the other direction. The dot want to go to the other direction. So, but however, if you when we do the co-optimize the cost and the reward, the dot want to go to this direction. However, this is infeasible. So this is actually the risk for us to train the safe reinforcement learning, because this temptation. So we say all the tempting policy. The tempting policy means all the policies that have a high reward than the optimal policy. So we say all the tempting policy are unsafe, because this is it's clear in this case. We will now discuss in this case. In this case, there is no tempting policy. So that's kind of a trivial case, because this is a to do optimization. In this case, you do not need a safe RL. You just need the traditional RL, and find the optimal policy is naturally satisfy this constraint. So if this boundary on the right is not positive, it's negative in this case, then we call it a trivial safe RL. Then the number 2, so optimal policy of temptation is of the tempting problem is on the boundary. So we say because now this optimal policy is on the boundary, so we will have some robustness issue always for safe reinforcement learning. So yeah, so you can see this is a normal case without disturbance. We can still learn this policy just as what I showed. So however, if you have certain attack, adversary attack, meaning you have perturbed the observation, then the training can be very problematic. So in other words, the CAPO, what we showed in our just now, is optimal and convex and feasible. They have all the good nature. However, is not robust against any attempt, any attack because of such a phenomenon, because of the nature of the safe RL. So how to do that? So first, let me try to introduce what is the observational attack. Observational attack is poisoned. The observation of the attack is poisoned or attacking in this way. So whenever we have the observation, so we have put some noise to this observation and then put a policy here, right? So then now is instead of working on the real state, we have a perturbation of the state. And then after that, we have this poisoned value function. So in this case, the true state is not modified. We only have the observation problem. So this is a very how to say, very practical and realistic. Because for example, if I have a self-driving car, you may tilt the camera or have pin something on the camera. So the other cars do not change, or you can spoof the GPS. So the other cars may not change. However, your because this the attacker can just try to attack the sensor, and we will have this observation attack.
Professor Zhao, can I ask you a question?
Yeah, go ahead.
Yeah, I have a question regarding to the safety guarantee. So I see your example is relatively simple, right? But in practice, there are many open environment. For example, the robotics in different rooms. The state space are different, so in different rooms. So in this case, can we still have the safety guarantee?
That's a very interesting question. So you're talking about non-stationary environment, right? Okay. So yeah, so I can jump to another paper I want to mention later on. So for example, if you have this is another paper. It's called the Safe Reinforcement Learning for Non-Stationary Environment. So in this case, it's not the room, but so the goal of this robot arm is to feed some medicine to a patient. It's actually a very difficult problem because this patient, the pattern of the movement of the head change all the time from different patients. So if someone have Parkinson, and then usually have the head is shaking and the head is shaking and the hand is shaking. So and also the shaking pattern usually very different. So in this case, if this robotic arm try to learn how to feed the medicine to the patient, you need to learn different this shaking pattern. And in this case, we need to have this paper called context-aware safe reinforcement learning. So on top of the safe reinforcement learning, you also need to have a context. Context basically means you say in your saying is the say different room. So you need to give me additional information. So am I driving in China? Am I driving in Beijing? Or am I driving in, say, Hong Kong? They may have very different pattern, right? So I need additional information. So driving in Hong Kong is driving on the left, right? So that's very different. So I wonder if a car trained in Beijing can directly, I doubt whether that can directly drive in Hong Kong. So we need to have this additional information called context information. And then we can put this context information into this called the context-aware model, where we are using this model called neural process. It's a combination of neural network and stochastic process. And combine this, we can learn several policies. You can see this is several policies and use a self-attention mechanism to choose which one to use. So this is a combination of the safe reinforcement learning and also generalizability of the reinforcement learning.
Thank you very much. Yeah, thank you very much.
So let me switch back. Okay. So then let me try to finish. Okay, so now we understand what's the observational attack. So what are the good attacks, meaning effective attacks, so that we can use those attacks to train our policy. So the attack need to be effective. So there are two criteria. So one is effectiveness. So we want to make this agent unsafe. The cost need to be high. Another one is we want the stealthiness, make the agent unaware of the attack, meaning we want the reward. We can still want the agent to be able to finish the task. So if the agent do not finish the task, then we already know it's, for example, it's a car, it will crash. However, the agent does not even drive. So then it's also hard to notice. It's not also not a very effective attack. So in this case, we can still use this VCVR diagram to show this approach. So we want this JE to be positive, right? So that it's effectiveness, and also we want this stealthiness also to be positive, so that we can be both effectiveness and stealthiness. So okay, so can we directly use some off-the-shelf adversarial attack? There's a whole community called adversarial machine learning, and they develop all kinds of adversarial, particularly for supervised learning, but recently also to the reinforcement learning. For example, this is called maximum action discrepancy. So this attack. So this attack want to maximize the KL divergence between the policy of the clean reinforcement learning, the clean state, and also this poisoned or a perturbed state. So they want to maximize this too, so that the new action under this perturbation is different from the original action. Okay, so this is basically the concept of the maximum action discrepancy proposed by somebody else. It's effective to attack the traditional, the standard reinforcement learning, but we show it's actually very ineffective for the safe reinforcement learning. The reason is you can see this car is just run around. It cannot even work. It cannot even finish the task. So it will not touch, even we want the car to max the boundary, it may not be able to touch this boundary. So only make the agent stupid will not make it dangerous. Okay, so that's the interesting part for the safe RL attack. So how to do that? I think we published the first paper for the adversarial safe reinforcement learning. So the how to effect, so one way is a very straightforward way is maximum the cost, right? So we directly maximum cost. Right. So it's effective. So we just want to maximize the cost. So it will be better. Oh, sorry. Right. So that's a effective. We can maximize the cost. The other one, sorry, there's a typo. Should be MR. Maximize the reward. So this is actually a little bit counterintuitive. So how to attack a safe RL is to force it to have a better performance. So this, you can see this optimization goal is exactly the same of the standard reinforcement learning algorithm without considering the cost. So in our study, okay, so the attacker just need to do what a standard reinforcement to do to attack the safe RL. So you can see in this case, it's actually quite it's actually quite effective. So for both MC, maximum cost, and also maximum reward. And a lot of times, actually, the maximum cost is actually more effective. maximum reward is more effective. Okay, so after we have this effective adversarial, then we can train this safe IO. We can use the maximum cost, we can use the maximum reward, and also we can use both, a combination of both. It's become actually more robust. Okay, and we have some theoretical guarantee in this case under the Bellman equation. So I'll skip this quickly. And we create quite a few baseline because the baseline, the MID baseline is too weak. So we actually create some baseline ourselves. Okay, and we show that our approach is quite effective compared to other approaches. So, and we showed the comparison both in this car circle and also Zhong and aunt. That's a metrical environment. Right. So before the adversarial tag, you can see it still can follow. Now after this, the adversarial can after this adversarial training, even under attack, we can still almost finish this task. So it's not as good as clean without attack, but still we can almost finish this work. So it's become more robust. Okay, so some takeaway messages. So the safe file may not be safe under the adversarial perturbation. Okay, so if you train a safe RL, you deploy this to the real world, it's very, very sensitive to the noise. And the noise is everywhere. So this is the first takeaway message. Second, existing attack and defense methods are not effective for safe RL. Third, both maximum cost and maximum reward attack are effective. And we can have a combination of this work in our study. And the fourth is the adversarial training is helpful in improving the robustness. Okay, so that's the safe reinforcement learning. So in summary, I introduced how to evaluate the safety using some like accelerated evaluation approach. Second, how to design a safe policy, safe decision making, use reinforcement learning. We can use the convex optimization that use version inference. However, we noticed that this is not a robust. So we also introduced the robust safe reinforcement learning. Okay, so next topic I want to discuss about the generalizability. So generalizability, there's no consensus on how to define it, but somehow people have a sense of it. So for example, this is a video I downloaded from YouTube. And this intersection in Africa, it's in Ethiopia. And somehow this intersection is very interesting because you can see there are like 16 lanes and there is a big car, small car, buses, pedestrians, motorcycle. So it's actually pretty hard, and also people drive from all directions. So say for self-driving car, so if we can drive a car, if it trains the car somewhere, and if the car are able to actually drive in this situation, we'll see the car is very generalizable. So we hope that we train a car in Beijing and it can drive in, for example, in Shanghai, right? So that's somehow it's called generalizability. But we say, how about let's push it to the limit and see whether we can drive in this situation, how we can drive in this situation. So first, we need to have a model or have an understanding of this kind of traffic environment. So the challenge of doing so is that the number of the surrounding vehicles is actually time varying, right? So this is actually very challenging. Because so we first download the video and do some standard image processing and tracking to have the location of those cars. Then after that, we actually use some this is called hierarchical AI to process the data. In this case, we are using the Gaussian process for each local environment. In this case, because Gaussian process, you can define the covariance. So we have this covariance to model the local information. And then, but however, your local information keeps changing, so we need to have different setting of the covariance. In this case, we are using a hierarchical dirichlet process with a hidden semi-Markov model to sample how many Gaussian process we have for this environment. So then we can study this local environment. So actually, we started work, and I told my student I have the belief that there must be some pattern, because it seems crazy, but seems all the people there, living around this intersection, can drive in this situation. So there must be something that people can learn. So then we actually find a pattern for this intersection. You can see there are 8 main cases or scenarios for this intersection. And we say if you can handle this 8 main cases, then you should be able to drive in this environment. Okay, so this is basically the model of the environment, how to make the decision making. So we still use the structure of reinforcement learning to do so. So the first one is this is called task agnostic hierarchical reinforcement learning. So the concept is very relevant to what I just discussed. So basically, we have the Gaussian mixed model to model the environment. Okay. However, we do not know how to build the model. Particularly, we do not know how many numbers of Gaussian component to use. Right. So in this case, we need to sample the number of Gaussian components, and then we are using just still a hierarchical dirichlet process to sample the number of Gaussians. So dirichlet process will sample you a dirichlet distribution, and you have the weight for those Gaussians. So we deploy this approach to many, not only cars, but also applications, for example, robots and this medical environment, and also some intersections. We found it's actually quite effective. So this is actually one way to generalize using the hierarchical reinforcement, hierarchical artificial intelligence. Then you can automatically learn the patterns or scenarios of the environment. And then for each scenario environment, you train a policy, and you can switch the policy to that environment quickly. So that's what we did first. So another way to do so is to use you can also learn the model. You can learn some hidden representative information of the environment. For example, you can use a causal graph to learn the nature of the problem you want to solve. So in this case, what is difficult is usually the causal graph is a graph without information of time. It's some variable, and say A cause B and B cause C, right? So that's variable, but it usually does not tell you how long that A will cause B and how long that B will cause C. What's the time information, dynamic information? And usually dynamics is modeled as an MDP, right? So that's just a Markovan decision making. So how to usually that's also for example, in this case, so this model is a graph for this dynamic system, right? So because each step is a time step. So how to combine these two graph? How to combine the causal graph and also the dynamic graph? That's what we were thinking. So this paper actually gave a solution. So we say, okay, so we have some causal graph that represent the relationship between those variables. We have the MDP graph that tell us how the system will evolve. And then we can use the causal graph as a constraint to the dynamic graph, so that we know, okay, so those variables, when they combine with actions, some action and the variable, there is no irrelevant. It's irrelevant, no relationship, it's irrelevant. So then when we learn those MDP, we say those links will become, it's a zero probability. So we use the causal graph as a blockage for the MDP model. So then we can model these scenarios. And then, okay, so that's the model. Okay, again, how to design. So this is a published in Core this year, and also later on we published NIPS this year. So we can also use that for reinforcement learning structure. So for the reinforcement learning structure, for example, so the robotic arm want to stack the block. So you can train them in these cases, right? And the in distribution mean, okay, so it's also a 2-layer of block. And however, so it's basically similar to what we have been trained. The spuriousness, meaning, for example, we can change the color of those blocks, but the color actually has no relationship to the stack procedure. And then the composition approach, composition problem is actually auto distribution. Is that, say, if you only train this stacking robotics in this 2-layer cases, but you want to give the goal of the robot, say you want to stack the 3 blocks together. So how to do this? So this is actually very challenging for just traditional data-driven reinforcement learning, because most of the reinforcement learning, my understanding is that it just memorize what to do and it has a try and error and get some pattern. But it's really hard to generalize to, for example, you learn how to stack 2 blocks and you want the reinforcement to generalize to 3 blocks. It's actually usually very difficult for most of the algorithms. So this involves some logic in the reinforcement learning. But to describe every piece of logic to the reinforcement learning is very time consuming and sometimes infeasible for a human being. So what we do is say, okay, so can we learn this causal model? At the same time, we want to train a policy. So there are 2 steps in this policy. So with this intervention data, so we can first have this causal discovery block. We say, okay, so what's the relationship between those action and state, right? So we have a block on top of another block that's action, and the state is the height of the block is going up. And then we have such a causal graph. We impose this causal graph to this our dynamic model, and we can do this planning for the action. So this is a traditional, this is a standard reinforcement learning part. So, but before that, we have this causal discovery part, and we can prove that this causal, the whole loop can be effective and efficient in this paper. So we try this block stack problem, and also you can see this very classical navigation approach, right? So you have this agent that need to pick the key and go to the store. And we test that if you have trained that there is a 1 door, 1 key, can you generalize to two keys? You need to, or 2 doors, right? So you need to open 1 door and then open another door. So this actually can be also, it's very classical method that we have to use the causation. And another one is this how we can generate the safety critical scenario for driving. That's another case. Okay. And finally, as I already introduced, the generalizability also means you can generalize to non-stationary environment. Okay. So in summary, I introduced, okay, you can use a structural model for generalizability. You can also use this causation model to learn the system for generalizability. I also have other work on this online identification, this model, meta learning on the example model, and also use optimal transport for quick domain randomization, and another recent work on NIPS on curriculum learning. So, but today I think I'll focus on this tool. And this diagram is introduced in this survey paper on trustworthy reinforcement learning. So we just published a few months ago. So you can see we have agent, environment, and reward, and this three aspect is very important So for example, we want this agent to be robust to the environment. In the reward and the cost, once we add the cost, we can use that to represent the safety, meaning as a threshold. This robust means min-max the optimization against the uncertainty, and also the generalizability means this context is actually different for the inner training is different from the testing. Okay, so yeah, so that's what I introduced today about safety and generalizability. And most of work is supported by those companies, and we also have quite a few papers related to all the other topics. You can check our paper. So I start from evaluation as for safety, and then I go to robustness, and then I study the safety and generalizability, and now I'm working on the embodiment and also human centricity and explainability. For example, the causation can be considered as an explainability. Okay, and so for example, for this scenario generation evaluation, you need this. We have this another survey paper, and we have other survey paper for example, for this privacy of autonomous vehicle just published also a few months ago. You can check my Google Scholar. Sorry. Let me check the time. Maybe I think I will pause here. And just briefly talk about this embodiment. So the embodiment is very interesting to say how after you learn those algorithmic trustworthy reinforcement learning or trustworthy decision making, what's the problem to deploy that to the real world? I talked about the robustness already. However, there's other ways to make it even more challenging. For example, this paper we published in this year CVPR. It is say the work is the goal is very clear to say, okay, so you can see all those autonomous vehicles, they have sensors on top of the roof, right? And also one interesting part of it, one interesting phenomenon is you can see the placement of sensors look very different, right? So we want to study, okay, so in this case, if each company has a different LiDAR placement, and let's assume they synthesize all the LiDAR point cloud together, then how that will influence the ranking of the effectiveness of the deep learning algorithm that have been trained on some standard test, for example, KT dataset, right? So what we did is that we have some color scenario generation, and we in this color we have the bounding box, we have so we know where are the other cars, and we also can synthesize all the point cloud together with the sensors, and then we retune or retrain all the algorithms with this new placement of LiDAR, and then we define some surrogate metric because it's really difficult to do the optimization and evaluation of this by just the point cloud, because for every placement you need to retrain the reinforcement the perception algorithm. It's actually effective, very hard. So we need some surrogate metric to the object detection accuracy. So finally, we say we can get this multi-LiDAR configuration. So in this work, the result shows that for autonomous vehicle, it's actually very difficult to, for autonomous vehicle, if you change the LiDAR placement just by a little bit, that actually has a very different performance. It could be 15 to 20% difference if you just move the LiDAR and synchronize all the point cloud and retrain the model. So even though we have a rank of the point cloud perception algorithm like PointNet plus, however, and they have the rank on KT dataset, and usually the difference is like 2%. But if you move the LiDAR a little bit, the accuracy may drop by 20%. So after we did this, we wonder, it's really necessary to rank algorithm on one data set, because in this case, the difference only 1 or 2%, but in the real world, once you have a design of the car, the ranking will be very different. So that's what we think embodiment and put the put the machine learning in the real world is really important, rather than just stick to some standard competition. Second is say, okay, so we think, okay, have a different placement of LiDAR, just similar to move the sensor around, right? So say, in this case, how about we just put this camera on the robotic arm? And in this case, you can see this actually similar to move have different placement of the LiDAR, but it's a more dynamic. And we found it's actually very challenging for most of the perception algorithm, because it's a 3D world. And if you move the camera around, you will see different side of the object. And how to design a safe, certifiable, safe perception is actually unsolved problem. So I think our lab is also one of the first to study the 3D perception certification. Okay, so I think I will leave 10 minutes for Q&A. So those are the work I want to share about the safety and the generalizability of intelligent autonomy. Thanks.
Okay. Thank you very much for the talk. So is there any questions?
Hi, Professor Zhao. I'm
Yep.
Mingdong Wu, the second year PhD of Auto. Yeah, so I have a question about the scenario of your works. Did you consider the POMDP scenario in your works?
Good question. Currently, most of our work is still just MDP, not POMDP. For POMDP, I think it's more realistic because we may not know all the states. But usually, it's much harder problem. I would say very difficult to make a theoretical breakthrough for POMDP. That's my own opinion. So
Yeah, that's true.
Yeah. So, and also a lot of times we just assume we can somehow find all the key states, right? So in the real world, you can never find all the states, right? So it could be everything's linked together. So in theory, you have an infinite number of states for all the application. So and somehow you say, okay, so I know what are the important factors. So that's assumption. Well, there's some hidden POMDP. It's not a POMDP, but somehow kind of play the role for POMDP. For example, in my, as I said, so we may assume we do not know the causation. We know all the variables, but we do not know their relationship. Maybe some variable just useless variable, right? So just a spurious variable. In this case, we can use causal inference to remove those variables, right? So we assume we know say 10 variables, but not, let's say 100 variables. And we know now, we know they're all the possible variables. Okay, we don't want to study more variables. However, maybe only 20 of them are really useful, but we do not know which 20. In this case, we can use a causal inference to remove the other 80 variables. So this is another way to think about this problem. Right? So you can add more variables and remove some. So this is one. This is easier than say we do not know how many variables are there. Or we can only observe 20. So that's a setting. So I feel this is the second one is more, what I said is maybe more easier to achieve. That's one. Another one is if we, for example, in our cases, we use Gaussian process. So and we use derivative process to add more number component of Gaussian process. Right. So this is actually also avoid MDP POMDP issue, because say let's say we have a like I said, driving this SLP intersection is a crazy intersection, right? So in this case, we do not know how many variables they are because we do not know how to describe it. But we say, okay, so we assume locally, I can always use a Gaussian process to model the local information, which is reasonable, right? So for a small period of time. And then how many variables? If we say infinite Gaussian process, is also useless. So we need to have a finite number of Gaussian process. In this case, how to sample, we make the number of scenario a variable itself, and then sample that variable to find the optimal number of the scenario. Okay, so this is another way to solve the unknown problem.
Yeah, I see. I got the point that we can use some causal inference to reduce the problem to a finite and important variables. So in this scenario, the POMP DP may reduce to a MDP. Yeah, so the important variable are observable. Yeah, so in this case, yeah, we can make this
So the
assumption.
causal inference can remove the spurious variable, while the derivative process can add variables, can add the components, because it's add the mixture numbers.
Oh,
So,
I see.
So you have a structure, you have say like a 10 scenario, but you drive the car right in Beijing. You drive that for a month, and you say, okay, now I have 1,000 scenarios. You collect 1,000 scenarios in this case, but you know there should be infinite scenarios in the world, right? But the derivative process, the capability of derivative process is this. So, for example, in one day, you see a drunk person on the street. Every year, only once, right? So it's a very rare case. But then if you see a drunk person walk with zigzag, then the derivative process sample this scenario. Say, oh, this is actually very different. If you model this one with the old 1,000 scenario, then the error is too big. So I need to assign a new model to it. So the hierarchical structure, the hierarchical reinforced artificial intelligence will help you to add more variables. So you can remove the variable and add a variable, but POMDP sometimes assume you do not know anything. So you need a structure to do this. So POMDP somehow is too general.
I see. So I think your works are very rigorous and very theoretical, and the POMDP is exactly it's like a nightmare or a thrilling problem in RL theory. Yeah, as I know. So did you consider building some real system that can apply to some real applications, but regardless of the theory? Do you consider these types of works?
Yeah, definitely. As I said, our mission is to bring the theory to the real world. So I think that's the uniqueness of our lab. So we work on very theoretical things, but we also want to directly work on robot and with the human and with the healthcare. So some examples. So we work with the Uber to study their self-driving car and improve it. So that's one application.
Uber.
Yeah,
I see.
They have the world's first fatal accident with the pedestrian. And after that, I was invited to Uber and they work with me. And also, so let me reshare my screen. So you can see we have many other people. So Uber, we work with the Uber, we work with the Ford about their parking system. So parking, because every parking lot look very different. So you need the safety and the generalizability for parking. For Rolls-Royce, we are working on the security of the embedded system. For Toyota, we work with the hierarchical reinforcement learning. So how to have the brain of the city. And for Google, we are working with this robotic dog for some household assistant robot. With Amazon, we are working on this. You can see this. Two of my students working on this. This is called Amazon Astro. So this is a Amazon, it's already commercialized. You can buy this robot for $1,000 at the US. So two of my students working on this has very good performance. For Qualcomm, it's also we won the Qualcomm Innovation Award, and we are working on the scenario generation for self-driving cars like this. So there are some examples.
Oh, got it. I think it's really impressive, both the outdoor self-driving scenario and the indoor like healthcare and the indoor navigation of a robot dog. Okay, are both considered. So yeah. Okay, I got no question. Thank you.
Sure. We actually also work with the hospital about the diagnostic. For example, one of my students working with Apple, Apple Watch. So he used the information of Apple Watch to detect the heart attack. So there's I have another line of work about healthcare, but I don't have time to talk about it in detail today.
Oh, I see. Yeah, there's indeed a time limit.
Okay.
Okay, so thank you. And it seems that it's have been 12 o'clock. So
if I can leave here 1 or 2 minutes, but if other people have questions, other students have questions.
Hi, Professor.
Yep.
Everything, can you hear me?
Yes.
I'm a master student from Tsinghua. My name is Li Zhang. Oh, because you are visiting professor in Google Robotics, so I have a quick question. So recent months, there's a lot of labs including the industrial and academic. They propose some just like large models in reinforcement learning to just like some large language model like GPT in NLP. And recently, just like 2 weeks ago, Google proposed the RT1, large robotics model to have the generation ability. How do you think about this direction? It's just a general question.
Great questions. Several of my students also working on large language model. It's actually not very friendly to. I think they work on large language when they work with Amazon or Google, in the company, but it's not very friendly to professors in the university because usually we do not have the facility, and most of the time the algorithm itself is very easy. You just need a very powerful computer, and also need a lot of data. So it's more suitable for a company to do this rather than for example, for a professor, I think sometimes it's very difficult to work on very realistic problem. For example, build a bridge, right? So it's maybe the engineer engineer knows much better. So my thinking is this, my very personal, my own thinking about this is this. My own thought is this. I will still focus on more new concept, and only use the large language model as a tool in my application or in my research, but not study how to build a large language model. It's a very different area, and I think the scholars in big company are very strong because they have the facility to do this, and I personally do not. And usually professors in the university, most of the time they are not as they do not have too many resources as the people in the company, but I think they are very useful direction. So if you want to work in the company, I think that's a very important thing, and we should pay attention to it. But like like ChatGPT or other super large model, my understanding is that there is a lot of ad hoc algorithms, and it's not as clean as the traditional algorithm. So even a professor studied that there's something, it's really hard to prove anything for those model. Yeah, so that's my thought. I don't think I have a very good answer to that, but yeah, so that's some random thought. about it.
Sex, I know that RT1 and ChatGPT has a requires a lot of resources, and even the RT1 just like thousands and millions data by the Google researchers. It requires a lot of resources. But anyway, sex.
Sure. But I mean, language model itself, not super large language, like a medium-sized language model is still very useful, and we should also study that just LSTM, right? A lot of them just as LSTM. So it's actually a very good tool, and just like, for example, in control theory, or SLAM, there's a very traditional area. You should know the structure of it. But for research itself, it's a little bit challenging for me to do it. But they're useful.
Great, sex.
Great. Other questions? Okay. Yeah. If you have other questions, feel free to email me.
Okay. So
Okay.
thank you very much for the talk today.
Okay, great. So yeah, I hope next time we can see each other in person. Unfortunately, when I arrived China, we just opened, have a dramatic change of the policy. So it's hard we can meet in person this time. Great.
Okay, this is the end of today's talk. Thank you very much for everyone.
Okay, great. Thank you. Bye.